Uh, Dear students, today we are going to discuss about the Hall effect experiment. You know, Hall effect is an important experiment in semiconductors. This will allow us to determine the sign of charge carriers. Okay, whether we have holes as charge carriers or electrons are charge carriers, depending on the polarity of the Hall voltage. And this will also allow us to determine the carrier density. Suppose if holes are majority charge carriers, then we'll know whole charge density, carrier density, or if electrons are majority carriers, we'll also know what is the electron carrier density. And the effect is very simple. You know that means if you take a current carrying conductor, a semiconductor, and apply a magnetic field, transverse magnetic field, then there is a voltage which is developed, which is perpendicular to both the electric field direction as well as the applied magnetic field direction, and that voltage is called the Hall voltage. This is coming because there is a Lorentz force which acts on the charge carriers. Okay, so you see that the force experienced by the charge carriers in the transverse electric and magnetic fields is given by Q is the charge carrier, and V is the velocity of the electrons because of the electric field. V cross B is basically the applied magnetic field. So then it basically it experiences, suppose if we apply electric field in the Y direction, the force purely due to the electric field is given by QEY, and which is basically equal to if these charge carriers are flowing in the direction of X, okay, VQVX BZ is the where BZ is the magnetic field perpendicular to the magnetic field, and Vx is the velocity of the charge carriers in the X direction. So then the voltage that is developed is basically given by the Hall voltage, which is nothing but proportional to both the electric field as well as the magnetic field. The charge carriers gets deflected because of the Lorentz force in the Y direction, and the voltage develops across the Y direction, and the voltage that develops across this Y direction, if B is the thickness of this semiconductor sample that we are considering, then that is given by EYB, where EY is the electric field associated with that, and the VY is the voltage, Hall voltage. So how do we get it? Basically we know that the current density, if you look at it, Jx is nothing but, if you consider a cross section here, which is nothing but NeVx. N is basically the number density, E is the electron charge, and Vx is the drift velocity of these electrons, which can also be written as Ix is the current flowing and divided by the A is the cross sectional area. Ix by A is nothing but your Jx, which is nothing but Ix by Bt, where B is the width and T is the thickness of the sample. So this is nothing but the A is the area of cross section which is given by Bt. So Jx is the current density. Okay, so we can equate now the electric field associated with the Hall voltage as given by Vx into Bz, which is nothing but Jx Bz by Ne. Okay, or I can write the Hall resistance, which is nothing but Ey by Jx Bz, which is also equal to 1 by Ne, where N is the carrier concentration. So if I measure the Hall voltage, I can estimate what is the RH. Thereby, I can actually get to know about Ne, or the carrier density. Whether the charge carriers will get reflected towards up direction or the down direction, which again I will discuss in the next slide, which determines the polarity of Vy, which in turn determines the charge carriers, the nature of charge carrier. That means whether you have a p-type charge carriers or n-type charge carriers. So the measured Hall voltage, as you can see, is nothing but Rx Ix Bz by T. Okay, and you know that in semiconductors you have basically the conductivity can be written as because it has both positive as well as negative. That means electrons as well as the holes as charge carriers. So it can be written as the electron carrier density multiplied by the charge of the electron multiplied by the mobility of the electron plus the whole carrier density multiplied by the charge multiplied by the whole mobility. Okay, so in doped semiconductors, if we consider a p-type or n-type semiconductors, only one of them will dominate, and correspondingly the conductivity or the is determined by the majority charge carriers. So in this experiment, what we do is we'll basically try to measure the voltage in this direction by applying by setting up an electric field and applying a magnetic field perpendicular to that to a semiconductor material. And the measured voltage that you see is not only it consists of the Hall voltage, but there are other contributions that we need to take into account. So the other contributions are the measured voltage consists of the Hall voltage, of course, plus there is an voltage arising because of the thermo EMF, which arises because the points where we are measuring, if there is a thermal gradient between those 2 points, then there is an associated thermo EMF. And then since these charge carriers are experience the magnetic field also, there can be a resistance or the voltage corresponding to the purely because of the magnetic field, which basically gives rise to a magnetoresistance contribution. So one has to take into account these 2 contributions are correct for them before estimating the Hall voltage. So the experimental setup consists in this fashion, which I will show you in a few minutes, that you have a 2 electromagnet through which you, by passing the current, you can actually set up the magnetic field. And in fact, you will use a Gauss probe to measure the strength of the magnetic field, applied magnetic field. So in the same experiment, you are using the Hall probe to measure the magnetic field as well. The sample is kept in between the pole pieces, through which you have basically you can set up the electric field, and you measure the Hall voltage in a direction perpendicular to both the electric and magnetic fields. So as I told you that the thermal gradient or thermo EMF comes because of the ideally speaking, these 2 points where we are measuring the Hall voltage should be on the same potential, the equipotential surface. But how much ever care we take, there can be a small potential gradient that can give rise to some offset voltages. So first one has to make sure that the points where we are measuring are exactly on the same equipotential surface by adjusting the probes to be in the same equipotential surface. And then after doing that, we can actually pass the current through this measurement. But because of the passing through the current through the sample, there can be the sample, depending on the finite conductivity of the sample, there can be a gradient in the sample, the temperature gradient. And if there is a temperature gradient, there is an associated thermo EMF. So there is a thermo EMF one has to take into account. But apart from that, when we are actually passing through the electrons or the charge carriers, electrons or holes, they are passing through the sample, and if you apply a magnetic field, these charge carriers will experience a Lorentz force. Because of that, they traverse a longer distance to reach the terminal. In the process, there will be more collisions, and due to which there can be a magnetoresistance. So one has to account for the magnetoresistance contribution also, apart from the Hall voltage that you are measuring. So one has to take it into account. So the experiment to measure the accurate value of the Hall voltage, one has to correct for the thermo EMF as well as the magnetoresistance. So how do we go about it? For correcting the thermo EMF, you simply need to change the direction of the electric field or the direction of the current from I to plus X to minus X. By doing that, what you are doing is the measured Hall voltage, if you see the measured voltage, actually which consists of also Hall voltage, which is given by this, plus the thermo EMF, plus the magnetoresistance contribution. Basically, I is the current we are passing and Rm is the resistance, magnetoresistance contribution. So this voltage also is contributing. So when you change the direction of the current from I plus I to minus I, you see that the Hall voltage is also changing sign, and also the magnetoresistance contribution is also changing sign. But the thermo EMF contribution, which is independent, where from which direction the current is flowing, will remain the same. So if you now subtract these two fellows, you can get rid of the thermo EMF. So basically what you do is Vy plus minus Vy minus by I plus minus I minus. If you do, then you only get a Hall voltage plus the contribution due to the magnetoresistance. So this eliminates the thermo EMF contribution. So how then the next step is we need to eliminate the magnetoresistance contribution. So how do we go about that? What we do is we can actually now change the direction of the magnetic field. So from plus B, if you change the direction of the magnetic field, you see that when B becomes minus B, the Hall voltage is now, you see, is given by minus RHBI plus V thermal. Of course, we can take it, we can get rid of by changing the current direction, plus IRM we got. And when we change now the current as well as the magnetic field direction, so V by minus B, you see that this Hall voltage now, because both are changing sign, it becomes positive, whereas this magnetoresistance contribution is only becoming negative now. So if you now add these two fellows, okay, so V by plus minus V by minus, in fact again you are subtracting it out so that you can get rid of these contributions, and this you only get contribution because of the Hall voltage. So you can actually take now delta R is given by R prime B minus R minus B. So this gives you 2 times the Hall voltage contribution, and you can you plot now delta R, which is nothing but the resistance or the resistance corresponding to the Hall effect when the field is in the plus B direction, minus the resistance corresponding to the Hall effect when the B is in the negative direction. So the difference of this, if I term it as delta R, this gives me 2RHB by T, and if I plot delta R versus B, then you see that it will be a straight line, and the slope basically gives you that is given by 2RH by T, because you are plotting as a function of B, so the slope is nothing but 2RH by T. And you may ask why this is not going through origin. See, in principle, when B is equal to 0, there should not be any kind of Hall voltage, because there is no Hall effect. The Hall effect will arise only when you have transverse electric and magnetic fields. So when B is equal to 0, it should pass through the origin. So the fact that if it is not passing through the origin, this is arising purely because of the offset voltage that I described earlier. That means the two probes that we are using to measure the voltage in the y direction are not on the equipotential surface. So if there is any offset between these two voltages, then the corresponding resistance will give rise to that between the 2 points. Proportion to that, there some voltage will appear, which is called the offset voltage. So the intercept on the y-axis basically tells you what is the offset voltage that you have. And typically the offset voltage actually should be as small as possible, or ideally speaking it should actually go through the origin. And if you measure the slope now of this experiment, then that gives you, that will estimate now RH by 2RH by T thickness of the sample is given to you. So which you know that from the first slide, RH is actually gives rise to 1 over NE. E is the charge concentration, the charge of the electron. So you can basically determine the N. So you'll be able to estimate what would be the charge concentration. So the measurements that you are doing is basically you set up a constant magnetic electric field by passing current through the probe, and for different values of B, that is the magnetic field. So how do we change the magnetic field? By changing the current through the by electromagnet. So by changing the current through the electromagnet, we can vary the magnetic field, and then we can measure Vy plus and Vy minus by changing the electric field direction. So for a given magnetic field, you measure, suppose let us say that you have applied positive current, plus x direction the current, then for a given magnetic field I will measure what is Vy plus, and then for the same magnetic field, by varying the current from x to minus x, I can vary what is the corresponding Vy minus, and then I can actually calculate what is the Vr plus and Vr minus, and I can actually measure R prime B. That means for a positive magnetic field, what would be the R prime B? So by taking the difference between these two fellows, I can actually determine R prime B. Now the second part basically consists of changing the direction of the magnetic current. That means you are reversing the magnetic field. So if you do that, then again you can measure Vy plus and Vy minus for two different electric field directions, and corresponding Vr plus Vr minus you can measure, and R prime minus B you can measure, and the difference of these two fellows gives you delta R, which you plot as a function of B. Okay, for a given B, you will be able to calculate delta R, and then you can summarize that and then plot delta R versus B, and the slope gives you the carrier concentration. Okay, so how do we actually determine what is the direction? So you have to use the Fleming's left hand rule in order to determine the charge polarity. So if you say that if your electric field is given by your forefinger and your magnetic field is given by your middle finger, then the thumb gives you the force on the charge carriers. So if we'll assume that electrons are charge carriers. Let us say the electrons are flowing in this direction, and if the magnetic field is in this direction, and the force experienced by the electrons is along, say, plus that direction, then if you measure the voltage, then this point should be negatively charged with respect to this. That means if I measure Vy now, that should have a negative polarity. If that is true, that means the charge carriers are now electrons. On the other hand, if the charge carriers are positive, then the deflection will allow that the positive charge carrier, that means the holes gets accumulated in this side. In comparison to this gets positively charged, and if Vy is positive, that means the charge carriers are holes. So from there you can determine the nature of charge carriers, and from the slope you can determine whether what is the concentration of charge carriers. So the procedure is very simple. So connect the circuit. You have to connect the circuit. I'll show you in a minute. Set something like 3 milliamps. It can be like, to set up the electric field. So you set up some current through the sample. So this current remains constant throughout the experiment. Okay. So this current remains constant. But initially, to measure, to know that what we are setting up is correct, we can measure the we can set up the current and measure the voltage drop across the same terminal to see that it behaves the ohmic behavior. Okay, so you can set up the current after establishing that it is in the ohmic region. Then keep the sample outside the electromagnet, so don't apply any magnetic field, and check for offset voltage. That means you pass the current, and then without any application of magnetic field, you measure the voltage between C and D and make sure that this voltage is less than 5 millivolts. It's preferable that it's as small as possible. If this voltage is very small, then you know that your offset voltage is very small. And again, I'll explain you that the C and D points, let us say, are the points along through which you are measuring the Hall voltage. So if ideally speaking, if C and D are on the same equipotential surface, that means there is no resistance drop between C and D, then there should not be any offset voltage. But in a real situation, these 2 points may be separated by a small, however small it is, small distance. That means in that case there can be a finite voltage drop between C and D that gives rise to the offset voltage. Now we pass some current through the electromagnetic coils to set up the magnetic field, and initially, of course, to set up the magnetic field direction, see, because I need to know whether the magnetic field is in this direction or in this direction. Based on that, the Hall voltage, the charge, the force of deflection will depend. So I need to know whether the magnetic field is along, say from let us say from this direction, okay, into the magnet, into the sample, or outside. It's okay, it is coming out. So for that, what I need to do is I set up a small current, and then using a bar magnet or I can use a deflection magnetometer, and I can see that what would be the direction of magnetic field. Okay, so I know if I know the bar magnet, okay, which one is my north pole, I can see whether it is getting attracted or deflected, repelled in the between when we are placed in the magnetic field. So I can set up the magnetic field direction. Then once I know the direction of the magnetic field, then what I do is I can I know what would be, I know what is the, if I measure what is the voltage between C and D and what is the polarity, I can determine what is the nature of charge carriers. Then what I do is I actually use the orientation of the Gauss meter. I have to adjust to measure the accurate value of the field that is seen by the sample. I have to apply the Gauss meter orientation. The Gauss meter has to be adjusted such that I measure the maximum voltage. Otherwise, if the Gauss meter is making some angle, then I am measuring only the component of magnetic field, not the actual magnetic field seen by the sample. So I have to maximize the current by adjusting the Gauss meter orientation. Okay, or I have to maximize the magnetic field value by adjusting the Gauss meter orientation, and then I can set up the magnetic current through the sample, through the coil, and magnetic current to set up the magnetic field. And for different magnetic field values, I keep on varying. I keep on measuring the Hall voltage, but every time for a given magnetic field, I reverse the polarity and then again measure the Hall voltage. So I can do that using a DP/DT switch. This switch is called double pole double throw switch, which will enable to reverse the direction of the current. That means the electric field direction. If I want to reverse, then I can do that by using the DP/DT switch. So you people should also know that how the DP/DT switch connection works. So now what I will do is I will show you the actual experimental setup and then show you that how to carry out this experiment. Okay. Hello. The experimental setup that consists of Hall effect experiment is here, and we see that there is an electromagnet. This is the power supply to energize the coil, the electromagnet, and then the most important thing is this is the sample for which we are going to determine the charge carriers and the nature of charge carriers, carrier density as well as the charge carriers. So what you see is the rectangular strip. Here is the semiconductor sample. Okay, either it can be a p-type semiconductor or n-type semiconductor, and the two probes that are connected to the sample, you can see that is used to apply the electric field. Okay, so you pass a current through these probes, okay, connected through this here, then you can set up the electric field. Then these two probes which are transversed to that, or let us say C and D, are used to measure the Hall voltage. Okay, so what you do is this sample in this geometry, this geometry is kept in between the pole pieces. Okay, the way in which you can see here is that it is kept in between the pole pieces so that the electric field is passing through this, and then you have basically transverse magnetic field. So you can basically, like a Fleming's left hand rule, this is the direction of my electric field, let us say in this direction, and this is the direction of magnetic field, and depending on the charge carriers, whether it is electrons or holes, there will be a force experienced perpendicular to these two directions, either in the plus z direction or negative direction, negative z direction, so that there is a voltage which is induced, and that is the voltage that we are going to measure. It's called Hall voltage. So for that, what is required? We have to set up, we have to pass the current through the sample to set up the electric field, and we see that this is the Hall effect setup through which we can actually set up the current. As I told you, we can pass something like 3.55 milliamps current. Okay, so the same thing what I can do is I am using this circuit here, which is called the DP/DT double pole double throw switch. So DP/DT switch, through which I will be able to reverse the direction of the current through the sample. So what you do is you are actually measuring here the same current. Here this is the voltage that I am applying to set up the electric field, and the same thing is measured across a resistor, 1 kilo ohm resistor here connected in the back of this board, which is measured using a digital multimeter. So you can see that this is the current which is associated with the electric field. Okay, independently you can measure what is the current that's passing through the sample. And if you want to change the direction of the current, you simply have to now, by using the switch, you see that the direction of the current is now changed from plus to minus. So that means the direction of the current, either current is going this way or coming towards me. So I can actually always change the direction of the electric field. Okay, and to change the magnetic field direction, actually to measure the magnetic field, I am using a Hall probe. Okay, so this is a Hall probe which is kept at the same place where you have sample is there. Okay, in fact the sample has to be moved back a little bit in order to see that it experiences the sample experiences the magnetic field, and at the same position you have to keep the Hall probe. Okay, so the Hall probe is connected to a Gauss meter. Okay, so this is a Hall Gauss meter, digital Gauss meter. Okay, so through which you can measure what is the magnetic field strength experienced by the sample. And another important step that I told you earlier is that to change the magnetic field strength, so we have a power supply which is used to pass the current through the coils. So by changing the current through the coils, you can see that the magnetic field in the Gauss probe meter, you can see that the magnetic field is actually varying. So you can actually vary, and then correspondingly if you see the voltage, Hall voltage that you are measuring here, okay, this is used here, you are measuring the Hall voltage, you see that the Hall voltage is actually changing proportional to the magnetic field. Okay, so initially we'll switch off the magnetic field. We do not apply any magnetic field. We do not, in fact, it is better that you can actually take out the probe and only apply the electric field and measure what is the voltage that is there in this setup. So you can actually take it out and then measure what is the voltage that is there in the across the Vy. Okay, so that voltage is nothing but like, let us say this is like 1 millivolt. So this is like a offset voltage I was discussing. Okay, so this is the offset voltage that is experienced by the sample because of the because C and D are not exactly on the equipotential surface. We tried our best. We can actually address them. I mean adjust them by so that they lie in line. Okay, so in a equipotential surface. So but still, if there is a finite resistance between these two probes, so then that appears as an offset voltage. So after having adjusted the offset voltage to minimum value, then you set up the electric field and start applying the magnetic field. So you can fix value of magnetic field you can apply, and then measure the Hall voltage. So you can apply. You can apply a fixed value of magnetic field, and the magnetic field strength can be measured at the Gauss meter. So for different values of applied magnetic field, you can measure the Hall voltage for a given magnetic field by reversing the direction of the magnetic field. Again, so electric field, you can again measure the Gauss Hall voltage. Okay, so you keep doing this for different values of magnetic field, and after finishing in one direction from 0 to the maximum value, then you come back and then you can reverse the polarity of these two the polarity of the power supply, so that the magnetic field now is in the opposite direction. But I think I forgot to tell you that we need to establish whether the magnetic field is in this direction or in this direction. For that, what I do is I can actually apply a small magnetic field, and then by checking with a bar magnet, I will be able to establish whether the magnetic field is in this direction or in this direction, because this is important. Once you know that, because you establish that the electric field is in this direction and magnetic field is in this direction, let us say, and if the force on the charge carriers is along plus that direction, then the polarity that you expect, if the electrons are charge carriers, then Vy should be negative. If the holes are charge carriers, then Vy should be positive. So through that you can actually estimate, and after establishing that, for different strengths of magnetic fields, you can measure the Hall voltage and plot. Okay, after taking the difference between Hall voltage that is measured for positive magnetic field to the negative magnetic field, you can measure delta R and plot delta R versus B, and from the slope you can determine what is the Hall voltage. Hall voltage, and which in turn give you, which is proportional to basically, which is nothing but 1 by Ne, and you can calculate the carrier concentration. Okay, so what I am going to do is I will share the data which is collected previously, okay, for different magnetic fields, what is the Hall voltage with you people, and you are supposed to now do the algebra in order to take care of the thermo EMF contribution as well as the magnetoresistance contribution, and estimate what is the actual Hall resistance for a given magnetic field, and plot delta R versus B, and then also estimate from the graph, estimate what is the offset voltage, the given experimental data, and then calculate what is the carrier concentration. Okay, so this is what you need to finish the thing and then submit the assignment. Okay, thank you.